We are continuing on with our outline, kind of factors affecting rates, but we're at number 2 now. So our first factor was reactant concentrations, and number 2 is temperature. And pretty much the rule of thumb is for every 10-degree rise in temperature, the rate approximately doubles. So I'm just going to write that plus 10 degrees Celsius equals 2 times change in rate. Again, you will see delta all the time. That's just going to be our shorthand for change. And letter A, collision theory. Collision theory. And collision theory says that molecules must physically collide. So collision theory says that molecules must physically collide with the correct geometry correct geometry and sufficient energy to react. So for a reaction to take place, 3 things have to be present. They have to touch each other, in the correct orientation, and they have to have enough energy when they hit each other for the reaction to proceed. Alright, so a couple things. 3 things must be present. We're just going to underline those. They must physically collide, so they actually have to hit each other. They have to have the correct geometry, so they have to hit each other on the right sides of the molecules, the correct sides. And they have to have sufficient energy to react. We're going to kind of break this into 3 kind of subpoints and kind of take these one at a time as we go through our notes today. And number 1 is going to be frequency. And this really gets at them actually colliding, so the physical collision. So how often do they collide? And if we kind of go back to temperature is what we're talking about, if we increase the temperature, so increase T, really means increased kinetic energy. Because what is temperature? Temperature is a measure of the average kinetic energy of a substance. So if temperature is going up, it must mean the kinetic energy of the substance is going up. If kinetic energy is going up, then it also means that our velocity is increasing as well. Okay, so the speed of our molecules is their kinetic energy. So increased kinetic energy means increased velocity, and increased velocity means increased collisions. So if as the temperature goes up, what happens? They hit more often, which means our rate, our reaction, should happen a little bit quicker. Okay. Number 2, we are going to look at the energy. So it's not going to actually be in order, but the sufficient energy portion. So energy. And we are just going to kind of come up with some just generic equations here in a second, but we're going to call them the reaction pathway. And in our first one, we're going to have A, and it's going to react with BC. So A plus BC. And during the course of this reaction, we make something in the middle. It's going to be called an intermediate. You'll have a little bit more notes on this in AP Podcast 2.4. But we have something that's A, sort of bonded to B, sort of bonded to C. Okay, so it's kind of a dashed line instead of a full line. There's a bond forming, there's a bond breaking there, and this whole thing yields AB plus C. Okay, so a single displacement reaction where B is essentially changing partners. Alright, and that happens. Alright, we can also say that A plus BC yields, it's going to be the same intermediate, A dash dash B dash dash C, and no reaction takes place. So sometimes we can react things and they react, we get products. Other times we can try to react things and we are just left with reactants. So what is the difference in these 2 things? Alright, it would be the first one we would say has enough kinetic energy, and the second one obviously has not enough kinetic energy. And I am just going to pause right here And a good example of this would be if we had a hydrogen balloon, or if we just released hydrogen into the air. Do hydrogen and oxygen react with each other? They do not. If there is a spark of fire, if we add a flame, what happens when we react hydrogen and oxygen? They explode. Okay? So in the first instance, with flame, they have enough kinetic energy. We're adding enough energy that they actually react with each other. But in a normal circumstance, hydrogen and oxygen, they're both in the atmosphere, they don't react with each other. And why is that? One has enough kinetic energy and the other does not. This ABC, we kind of talked about it a little bit already. And I apologize, I completely lied earlier. I said intermediate, and in AP Podcast 2.4 we will be talking about intermediates, but this is really our activated complex, or another name for it is the transition state. Alright, so this is not an intermediate, my bad. We will talk about intermediates in our next podcast, but A-B-C is the activated complex, or the transition state. And the transition state has really high potential energy, alright? Which is going to lead us to potential energy diagrams. Some of you may have seen this in general chemistry or college chem, others of you have not seen this. But a potential energy diagram is essentially potential energy is graphed on the y-axis. And then on the x-axis, we basically have elapsed time, we have reaction progress, but essentially this is just over time is on the x-axis. And we plot something kind of like this. On the left we have our reactants, and on the right we have our products. We're going to kind of expand this and look at a couple of these from your book. So this is figure 1317. I've changed the letters to kind of match the notes that we have above. But we have A plus BC, and A plus BC is our reactants. And over on the right we have AB plus C, which is our products. And notice, in order for us to go from reactants to products, we have to get to that transition state, which is at the very top. In order to get there, we have to climb that hill, and this hill is basically known as activation energy. So we have to supply energy enough for our reactants to get to the top of this hill where our transition state happens. Once that transition state happens, and there's just enough energy, it pushes over the hill and we get products. If we were to almost get to the hill, we could fall back down, kind of like I just showed, and we have no reaction happens. The reactants we start with are the reactants we end with. But again, if we have a sufficient activation energy, or sufficient energy, our activated complex, or our transition state, happens and it turns immediately into products. These potential energy diagrams relate directly to delta H, which you should remember from general chemistry, which is essentially enthalpy, or it may have just been told to you as heat. But delta is always final minus initial. So in this case, if we have products that have a small number, and reactants that have a relatively large number, when we subtract initial from final, we get a negative value. Alright? And over on the other hand, we again have an activation energy. Notice it's a much larger hill. We have to supply a lot more energy for this one to happen. But our products have more energy than our reactants, and this is known as positive delta H. And positive delta H is endothermic. So again, negative delta H, exothermic reactions. There's heat left over at the end, so it's given off, or it's lost. In delta H, it requires heat, so heat goes into our system to make up for that huge energy of activation. What is the delta H, really? Because it's final minus initial, it does not take into consideration the EA, but it's just the change from our final state and our initial state. And we'll talk a lot more about delta H's when we talk about thermochem, which is going to be happening right before Christmas. But again, potential energy diagrams. Just wanted you to see that and hopefully relate to something that you learned in general chemistry. And our last thing, we've kind of talked about frequency and energy. And our last thing is going to be orientation, alright, which relates to geometry from our definition on collision theory way up at the top of the notes. So orientation. And this is orientation. This is really just the direction the direction of collisions. And because molecules exist in 3 dimensions, when we write them on paper it's fairly obvious, left hand, or left side, right side, top side, bottom side, but in 3 dimensions there is no left, there's no right, there's no top, there's no bottom. They are, if it's gas, it's just moving through space, flipping through space, and it's hard to really define top, bottom, left, right. Alright, so we're going to try to do our best on 2 dimensions. So we have A plus B, and then we have our activated complex there in the middle. A dash dash B dash dash C, and that's the equation you've seen before. If we had A plus CB, it's the same compound, but we're just going to attack the left side instead of the right side. Okay? So in this case, A, when it reacts, because A is not able to form any kind of bond with C, no reaction happens. So if these molecules hit A to C, there's no reaction, but if they hit A to B, there is reaction. Okay? So again, I'll try in class tomorrow to have some sort of kind of visual for this. But again, here's the best visual we can do. This again is another graphic from your book. But A can react with, or the orange ball can react with the purple ball, because they are what is our product on the left-hand side, potassium iodide, so that happens. But if our potassium hits the CH3 portion of the molecule, there is no reaction. Again, because the orientation is not correct.